Hi, welcome to 52 Weeks of AWS. My name is Noah Gift, and today we're going to continue to cover the Solutions Architect training material. I'm on the module 11, which is caching content. And let's go ahead and just dive right in here. I'm going to go ahead and share my screen here for people that are watching on video. And we can go ahead and get started here. So to start off with, I'm going to dive right into an overview of caching, talk a little bit about some of the key concepts here. So in general, caching is trading capacity for speed. And one way to think about caching is that it's a high-speed storage layer, right? And speed is really important because if you want to talk to the latest news or a product catalog or tickets to an event, etc. These are all things that you need to consider. And a cache is a high-speed storage layer. And what's interesting about it is that it trades the capacity for the speed, right? Because you're going to have to refill that cache constantly. A really good example of this on a machine would be RAM. RAM would be the fast memory, but your disk itself would be the bigger capacity. So that's a good intuition. So here's one example that comes from the real world is that if you have a house and you are doing lots of repairs on your house, or maybe you're renting out an Airbnb or something like that, you're going to have to make a lot of trips to the hardware store, or even building a house, right? That could be another scenario. If you make a trip every single day, that could start to add up and you're eating into the time where you could actually go ahead and build something. So instead, what you could do is you could build a storage unit right next to your house, and you could put the things inside of the storage unit that you'd frequently have to make a trip to the hardware store for. So that's kind of an intuition here behind caching. I think you could also say the same thing for working from home or commuting, right? It's the same thing. If you have to commute, 2-3 hours a day round trip, then that's all time that you can't spend making yourself healthier or learning things. And so it's just really a waste. And so by working at home, it's also a form of caching, right? Because you don't need to go that physical distance. So what should you cache? This is a really good question. In general, it would be things like expensive queries that are slow. Static websites are really good examples of this, like social media, news, where the stories really don't change that frequently. And also things like stock prices, that could be a good example of something that you could cache, or maybe like a metric for some kind of a data center capability, like the storage of your hard drive. It probably doesn't change that often. You might be able to cache that. Some of the benefits of caching are that it improves the speed of your application. It also reduces the response latency as well. And so this is also a really big one here, is that by being able to reduce the latency, you're going to improve the performance. And also you can reduce the application processing time for things like database access of a read-heavy system or a write-heavy system. Could potentially be cached, but those are typically less of a benefit. Really, it's the read-heavy applications where you get the best benefit from caching. So a really good example would be of caching is a simple web app that has accelerated retrieval of information from websites. You store a mapping of domain names to IP addresses. You accelerate retrieval of web content from web servers. You accelerate application performance. You reduce latency. These are all different things. Reduce latency to talk to a database. These are all things that caching can help. So let's talk a little bit about edge caching. So a good example of edge caching is that, when you make a call to a website, depending on where you're at, you could be hopping through lots and lots of routers. And so these are all locations where things could be optimized and you can improve the performance. A content delivery network is a globally distributed system of caching servers. Very common to use a content delivery network or a CDN to deal with things like HTML, CSS, JavaScript, image, video files. a CDN will deliver a local copy of that requested content from a cache edge or point of presence. And in particular, CDN is well suited for AWS, and they have one called Amazon CloudFront. And in particular, it deals with things that are either static or dynamic, and it's also self-service, pay for what you use offering. You don't have to sign a contract, etc. You just get a global scale CDN right off the bat. I personally use it for multiple kinds of websites, and it really is a great service. CloudFront provides both network level and application level protection as well by integrating with AWS Shield standard at no extra cost. And also, it works with custom SSL certificates as well. And so you get a full, end-to-end caching system that works very well with modern websites that require encryption and security protocols. And also, it has support for WebSocket protocol. And you can use a single domain to deliver an entire website through CloudFront, and you can accelerate both the download and upload parts of the website. So some examples of things that you could cache inside of, an edge cache would be things like the HTTPS protocol for the encryption of the user page. You can use CDN or edge cache to cache static content, including CSS, style sheets, JavaScript, image files, video files. Generally, the dynamic content is a little bit more difficult to cache or impossible, but you can configure CloudFront to deliver this information from an application that runs on a custom origin like EC2 or a web server. And you can also configure CloudFront to require that viewers use HTTPS to request your objects. So there is a way to configure both an EC2 instance and also CloudFront to work together to provide a mixture of both dynamic and static content. So CloudFront will deliver content to users through the CDN. These are the edge locations. So when a user requests content that's been served out via CloudFront, the DNS will route that request to an edge location that best serves the request. Typically, it's the nearest edge location, and CloudFront will check the cache for the requested content. That's step one, and then if the content's in the cache, CloudFront will deliver it immediately. So that would be right to step 4. The data is transferred to the user. The content may not be in the cache though, and so in that case, CloudFront will forward the request to the origin server as the source for the definitive version of your content. Step 2. The origin server will then send the content back to the edge location, step 3, and then CloudFront will forward that to the user. So basically, as objects become less popular, the locations may remove these objects to make room for more popular content. So that's kind of it in a nutshell, how caching works. So how do you configure CloudFront to host things? So you can specify an origin server. So it could be S3, it could be AWS Elemental Media Package, it could be a custom origin, like for example, EC2 instance or your own web server. So you can specify all of those, and then you can specify the details of how to track and manage the content delivery. And you can create access logs that show the activity, like cookies or query strings. And then CloudFront will give you a domain name, and then at that point you can send the distributions configuration, but not the content, to the edge locations. That's kind of it in a nutshell. I think S3 is the one that many people use, and it's probably the most intuitive initial way to use CloudFront. Now, there are some things to be concerned about in terms of using cache content, and one of them is time to live. And so TTL in this scenario, you would say you can control how long your files will stay in it before it forwards another request to the origin. If you reduce the duration, you can have more dynamic content. Increasing the duration means your users will get really good performance, but potentially there could be more stale content. Also, change object name. This is a method that requires more effort, but the replacement is immediate. You can update existing objects that use the same object names. And for example, you may want to update an existing object in your origin with a newer version that has the same name. In that case, the edge location won't get that new version from your origin until both of the listed events occur. You can also invalidate objects. And so this one is really a bad solution because the system has to be forced to interact with all of the edge locations. So you don't want to use this one that often. So example here would be a video on demand streaming service. So CloudFront does work really well with streamed video because it has all these edge locations. So what you could do is you'd first encode it and put it into a form that CloudFront can distribute it. And then at that point, you can actually set this up so that it will stream that content via CloudFront, right? So use something like AWS Elemental Media Converter and convert it to multiple formats, put that into S3, then tell CloudFront to listen to that bucket, and then it will be able to stream that content from CloudFront. So in general, you only want to cache the static content, but you can have content that appears static because of its URL, but is built dynamically the first time it's needed. And this dynamic build can be useful when the content is reusable, but it can be expensive to create and change infrequently. Map tiles are a good example. In this case, you cache places people frequently visit, but not places like remote areas. If you generated all the possible combinations of tiles, it would be expensive and wasteful because most would never be requested. So instead, you would basically, only dynamically configure them when necessary. The other thing you can do with CloudFront is you can improve the resiliency of an application by protecting it from a distributed denial of service attack, or DDoS. And so in order to use this, you actually get this capability as part of AWS and using AWS WAF. And some things to be aware of here is that the AWS WAF is a web application firewall and allows you to monitor both the HTTP and HTTPS requests that are forwarded to, let's say, API Gateway, CloudFront, or an application load balancer, and then you can control access to the content for it. So this would be a great example of how you could use the best of both worlds, both the web application firewall as well as CloudFront, to build really a global scale web application. And we can next here talk about caching web sessions. And so this is kind of a classic problem that happens many times actually in the game architectures. I've worked in game software engineering quite a bit, and this is one of the more classic problems. And in particular, I would say that this classic problem is interesting because of scalability. And so why do we care about this in terms of scalability? Well, basically, if you always have the client go back to the same machine, maybe that machine was actually very busy. And as a result, you could actually have not a fully load balanced scenario. And so one of the things to consider would be to figure out a way to mitigate that kind of an issue by having a more distributed sticky session, or a different kind of session. So in particular, this format of maybe caching the distributed sessions up front and keeping that into a global cache or a centralized cache is really an interesting idea, because then every time you want to go to a new instance, you don't have to remember the web server that you're already on. You just grab the data from the cache, which is globally available, and then you then use that information to do whatever it is you needed to do in the game. And so that is actually a very good point to consider when dealing with sticky sessions versus a distributed cache. And another place that you could store instead of a distributed cache would be DynamoDB, because by its own nature, it can scale up and down. It works very well for key value storage. A different kind of thing to consider would be storing session state for an online game application. And if you were going to do something like this, you could have the game request go into an ELB. You would have the web servers have auto scaling groups, so that would scale up and down. And then the game server itself would be its separate auto scaling group, and then basically the caching would happen with DynamoDB, which also can scale up and down. And so it itself would hold the state, and both the web server and the game server would not hold any state at all. And I think this is a pretty good architecture that I've personally used in different kinds of applications that I've helped build. All right, what about caching a database? This is a really common problem, and a database oftentimes is the bottleneck that kind of slows everything up. And one of the things to consider with caching a database is really how to do it effectively. So why would you want to do this? If you're concerned about response time for customers, maybe you have a latency sensitive workload. That's one way to consider caching for your database. If you have a high volume of requests that are coming into the database, you may want to, before you just send all that directly to the database, you want to have some kind of connection pooling plus cache that would really help protect your database from becoming like a queuing server. And then also, if you want to reduce the cost of the database, a cache could dramatically reduce that. So here's one example. Let's say you're using DynamoDB, which is a key value database, and you want to get a faster response. How would you do this? Let's say you want to go to millisecond scale response, and currently you have CloudFront, an ALB, application load balancer, a web server, DynamoDB, and then a game server. What could you do? Well, you could use the built-in Amazon DynamoDB accelerator, which is a fully managed, highly available in-memory cache for DynamoDB, and it allows you to have really performance microsecond scale response time. It's highly scalable, fully managed, and it's also integrated with DynamoDB, flexible and secure. So basically, one of the things about DynamoDB is it really included inside of it a great in-memory cache solution. And so they call this DAX or DAX, and you can actually use this to accelerate your response time to microsecond scale response time. You can also do things via remote or side caches. And in the case of DAX, it's a transparent cache, but another way to implement it is to use a remote or side cache. A side cache isn't directly connected to the database. Instead, it's adjacent. That's why they call it a side cache. And it's typically built on a key value NoSQL store like Redis or Memcached, and they can provide hundreds of thousands of requests, up to 1 million requests per second per cache node. And so they're used for read-heavy workloads in particular. So for example, a given key value pair tries to read the data from the cache. If the cache contains the value, it's called a cache hit, and the value is returned. The second scenario would be if the key value pair is not found, it's a cache miss, and the application will then go get the data from the database. And it's important that the data is present when the application needs it again. And so to ensure that, the key value pair that's obtained from the database is then written to the cache. So that's essentially the scenarios that caches go through. So one example of a side cache is Elasticache, and it provides web applications with in-memory data store in the cloud. And so it works on in-memory data store and cache, high performance, fully managed, it's scalable, and it also has two different kinds of backends. It has the Redis backend, and it also has the Memcached backend. So in the case of Redis, the Elasticache for Memcached, this can scale up to 20 nodes per cluster. And then in the Elasticache for Redis, it would scale up to 250 nodes per cluster. And so the Elasticache will run on the same reliable infrastructure as all the rest of AWS. And you can do things like create high availability or HA deployments by doing a multi-AZ deployment with automatic failover. So Memcached and Redis are simple caches that can be used to offload the burden for a database. And each of these have a slightly different advantage. And so in the case of sub-millisecond latency, both engines are able to do that, and they can read data quicker than a disk-based database because it's in memory. They're in terms of ability to scale horizontally, Memcached does allow you to do that, and you can scale in and out and add and remove nodes. Multi-threaded performance, because Memcache is multi-threaded, it means that you can use multi-processing cores. So you can actually have, let's say, a .NET application that, spins up a, pool of threads, and those threads go through and do a bunch of operations in parallel. In terms of advanced data structures, that's something that only Redis supports. Sorting and ranking data sets, Redis supports that. Also, PubSub or publish subscribe messaging, Redis supports that. And then in terms of multi-AZ deployments with automatic failover, that would only be supported by Redis. And then persistence, you can persist with Redis as well. And this enables you to persist your key value store. So in terms of Elasticache components, what are they? Well, a cache node is the smallest building block of Elasticache deployment. It's a fixed size chunk of secure network attached RAM, and each node runs the engine that was chosen when the cluster or replication group was created or last modified. And each node has its own DNS name and port, and it can exist in isolation from other nodes or in a grouping with other nodes, which is known as a cluster. So you can employ two different kinds of caching strategies with Elasticache. One of them would be lazy loading. So basically the way this works in pseudocode is that it first loads the data into the cache only when it's necessary. And then when your application requests the data, it then makes a request to the cache. If the data exists in the cache and it's current, the cache hit occurs, and Elasticache returns the data to your application. Otherwise, if there's a cache miss, then what happens is your application will request the data from the data store, which then returns the data to your application. Your application will then write the data to the cache so that it can be retrieved more quickly the next time it's loaded. So lazy loading, you use it when you have data that will be read often but infrequently. The advantage of lazy loading is it's only requested the data that's cached. And because most data is never requested, lazy loading avoids filling up the cache with a bunch of stuff that you're never going to use again. So it's a pretty efficient strategy. There's also write through, which is a second caching strategy. And this adds data or updates in the cache when the data is written to the database. So in these kinds of scenarios, your write through caching would, when you have like a necessary requirement for having things be real time. So let's say the top 100 scores in a video game, that would be a good example of this approach. And the advantage is is that it increases the likelihood your application will find the value of the cache when it looks for it. The disadvantage is you're potentially caching data that you don't need. So this approach can cause some additional costs. But the good news is you can actually use both of these scenarios together at the same time. So lazy loading is permits stale data, and write through ensures that the data is fresh. And so if you added a TTL value to each write, you can enjoy the advantage of each strategy and avoid cluttering the cache with data. So one scenario here where you would want to use this would be a 3-tier web hosting architecture, where you have a presentation layer with web servers, application layer with backend servers, and then you have a persistence layer. And so, in this particular example I'm talking about, it would be Amazon Route 53 would enable you to map your zone, like example.com DNS name to a load balancer DNS name. Then Amazon CloudFront will provide the edge caching. Then the load balancer will spread the traffic across web servers. And those web servers would be in an auto scale group, so they would scale up and down. And then the load balancer would spread the traffic as well across a backend application, and that would be in the application layer. And then the Elasticache would be the in-memory data cache for applications. So if you implement these multiple types of caches, you would get incredibly good performance in an architecture that requires incredibly good performance. So really some of the takeaways here are that a database cache would supplement the primary database by removing unnecessary pressure, and typically it will be the form of read. DAX is a fully managed, highly available in-memory cache, and Elasticache is a side cache. So there's a lot of fun things you can do with caching inside of AWS. All right, well, so that's it for me for today. I'm going to be out for a couple weeks, but I'll be back May 3rd for a continuation of our solutions architect material. And I believe I will be covering, let's go ahead and take a look here, what I'm going to be covering next session. It would be, let's see here, decoupled architectures will be covered on May 3rd. All right. Well, thank you, everybody, and I will see you May 3rd.